All right, welcome back to Math 1. This is Unit 2, Lesson 4, the in-betweeners. This is our homework help, so we're going to dive right into it. As always, if you look here, all the pink highlighted are going to be the homework questions. Anything written in pink to start these problems are things that could be helpful, and then anything else is just kind of me shorthanding to make sure that we can speed through this. So in our first two questions here, it asks us the sequences below exemplify a geometric pattern, fill in the missing values on the table, and then write an explicit equation for the pattern. For me, I personally always go through and I find the equation first, then I go back and I figure out, all right, what are all the missing pieces? So we did this on a previous video, so I'm not going to cover it. I went through and I used the pieces of information that were provided in this first problem, in problem 1, which was the sixth term was 64 and the first term was going to be 2. And I used that here as 64, here's my 2, and then here's my 6 from there. That minus 1 is just part of the equation, so we don't have to remember that. Now, we went through, I plugged into that purple equation, and we're going to go through and we're going to solve it out from here. We're going to look and we're going to say, all right, well, if we wanted to solve this, we divide both sides by 2. We get 2. What this gives us is 32 is equal to r to the 5th power. And then we can use our calculator to go figure out, all right, r, the 5th root of 32, and we get that our r ends up being equal to 2. And so from there, we can go build our actual equation here and say, all right, we've got our a of n is going to be equal to our first term, which is the 2 from here, by the way, times our rate of 2, x minus 1, or n minus 1 is also in there. And so we can get to there. From there, we know that our rate is going to be 2, so we're just going to go through and we're going to keep multiplying each of our last y values, or in this, the row is called value, and we're just multiplying our previous answer by 2. So we're going to get 2 to 4, 8, 16, 32, 64, 128, and then 256. And if you really wanted to, you could go plug into our purple equation down there. That is our explicit geometric equation, and it'll get the same numbers for you. But moving on to problem 2, we're going to do the exact same thing. I've already started this. We have in our orange, we have something already written out where we used these 3 values in our equation. We have our 45, our 360, and then our 4 located right there. So I'm going to backtrack through that, get rid of them, and we're going to go through and just kind of solve. So we said, all right, we're going to go divide by 360 because we're trying to get r by itself. What this does is this gives us, once we simplify, 1/8. Please don't turn that into a decimal. It'll just make life a little bit more complicated for you. So we get r to the 3rd power is equal to 1/8. We take the cube root of that. When we do that, I don't think I drew that on the last one, but I apologize. We get here, and we get that our r is equal to 1/2. And as always with mine, I circle things that are important but not yet fully done. So in this, we're looking at our equation. It's going to be a of n, or y equals, I'll do that in a different way just so that we can see it, is y is equal to 360, which is our initial value, times 1/2. I like putting my fractions in parentheses, all x to the minus 1st power. From here, what we're doing is we're cutting everything in half. That's what our r is. So we're going to do that starting with 360 to go to the next term. So when we do that, we say 360 becomes 180, 180 becomes 90, 90 becomes 45. Okay, so that all works out. Then we get into some decimals, 22.5, 11.225. Sorry, 11.25. Maybe I missed something up there. 11.25. Then we get into the 5.625, and then it gets even smaller, 2.8125. And that's us filling out that entire table. Now, we're going to move on to the next page here just because the start of it isn't anything bad. We can do that all kind of in one video here. In this problem, it doesn't give us a lot of context. It just says, all right, can we go through and break down these radicals? When we're breaking down radicals, what you're doing is you're looking for the perfect squares that go into them. So it'll likely be one number is the perfect square, and then after that, there won't be anything. So here, it's just factor trees for those of you who have done those before, but the factor trees must be perfect squares. So here, we're going to go through, we're going to say, all right, 25 and 3. And what that allows us to do is, what's the square root of 25? We get 5 with a root 3. And root 3 cannot be broken down anymore, so we're going to call it quits from there. Problem 7, ask yourself the same thing. What is going through? What's going to be the perfect square that goes in there? We can say root 9 times root 2. And then we do the same thing. The square root of 9 gives us 3 with a root 2 attached. And root 2 cannot be broken down any further because there is nothing, no other perfect squares that really go in there that can be broken down at all. Cool. All right, so we're going to move on to a little bit more of a difficult problem. So give us a quick second here to get that set up. All right, so if we scroll down to problems 9 and 10 here, which is still on page 2, just go down. There's a couple things that I just want to make sure that we know. Up here in pink, I have that x to the 1/2 power is going to be equal to the square root of 2. And normally when we write the square root of 2, we don't include either of these two numbers. They're not important because anything to the first power we don't care about, and we just intuitively know that a square root means we're taking the square root symbol is taking the second power of something. So I'm going to get rid of that. But I do have two things written up there. This wonderful symbol here just means therefore. So if you see that in any other future videos, that's what that means. So if x to the 1/2 power is equal to the square root of 2, therefore x to the 5/7 is going to be equal to the 7th root of x to the 5th power. And we're going to go through, we're going to play with that. We just have to match where our numbers are going, and we can do that down here. Now, for problem 9, it asks us to go through and fill in the missing values of the table based on the growth that is described, then to create the explicit equation for the table. Once again, I'm going to create my equation first because it gives us our first term, and it tells us essentially what our rate's going to be, because it goes, what is our first term here? What is our second term here? Our year 0 and year 1. And then we see, all right, we're looking at our y's, and we're saying, how does 2 get to be 6? We just multiply by 3. So our rate is going to end up being 3. So in this case, we're going to say that our y, or our a of n, if that's how you want to write it, is going to be 2, which is our starting, times 3, all to the x power, because we're doing an exponential here, not necessarily a geometric. So that's where we're going to end up looking. Now, then we start going through and plugging things in into our equation to solve the rest of this. Oh, we already used blue, so we'll go purple here. For the first one, we're going to go through, and I'm only going to do the first couple here. We get y is equal to 2 times 3 to the 1/2. Well, we just determined anything to the 1/2 is just saying the square root of it. So we're saying y is equal to 2 times the square root of 3, which is just y equals 2 root 3. So we're going to plug that in, 2 root 3. We're going to do one more of these just to make sure that we can kind of see a little bit of a difference. We've already used that color, so we're going to go here. We're going to look at 3/2. We'll do that over here on the right. We're going to say y is equal to 2 times 3 to the 3/2. Now, how I always go about doing this is I play around with those fractions, and I say, all right, well, we want to take out as many full numbers as we can out of there. So right now we're looking at 3/2 is just 1.5. We're going to remove a whole 1 out of there. So we're going to write it as y is equal to 2 times 3 to the 1st times 3 to the 1/2. Because by following our rules of exponents, 3 to the 1st times 3 to the 1/2 is just 3 to the 3/2, which is what we originally started with. And from here, we just clean it up. We say y is equal to 2 times 3 times the square root of 3, because 3 to the 1/2 turns into that. And then we get y is equal to 6 root 3. We can just go through and plug that in. Now, we could continue to do this with all the other ones. However, I'm not going to do that. You can go solve those the rest of the time with yourselves. But I will just put down what our answers is. If we're looking and we see a pattern, we see, all right, we go 2 to 2 root 3, 6 to 6 root 3, then we can assume, it's a dangerous game to assume, but we're going to say, hey, there's a pattern. We've got 18 root 3, 54 root 3. And then we're going to call that a day. We can go solve the rest of those using the exact other methods that we just talked about in the purple and in that yellow mustard color. But instead, we're going to move down to problem 10 here and keep moving on. So problem 10 is the same exact situation where we need to first come up with an equation that's going on here. They did add a couple more fractions in there in between, but we still have 1 point, 2 point. So we're able to say, all right, how do we go 2 to 6? We multiply by 3. So we know our rate is already going to be 3. So that's how we were able to fill in that 18 over there on the right-hand side, because we just said, all right, well, we're going 0 to 1, which is 2 to 6 times 3. 6 times 3 gives us 18, which goes over there. So our equation, though, that we're looking for is we're going to go through, we're going to write y is equal to our starting number, 2, times our rate, which is 3, to the x power. So very similar to our last, and in fact exactly like our last one, except for the fact that we're going to be using fractions that have a denominator of 3 instead of 2, which means we're taking a cube root instead of the square root. So when we go through and we look, we'll do these here. We're going to say, let's go look at 1/3. So if I go over here and I write y is equal to 2 times 3 to the 1/3, this is just going to turn into y is equal to 2 times the cube root of 3 to the first. Well, 3 to the first is 3, so we're just going to write this in as y 2 times the cube root of 3. And so we go fill that in, 2. I like putting the multiplication there just because it starts to look a little messy. It helps clean us up. We can do the same thing here with, I'm actually going to jump over to one of the bigger ones. We're going to look at this one here, 8/3. When we do that, we're going to go just like we did here. We're going to say y is equal to 2 times 3 all to the 8/3. But just like the above problem that we did in gold, we're going to say, all right, let's turn this into a way where let's pull out as many full fractions, as many whole numbers from that fraction power as possible. We look and we know that 3 goes into 8 twice, so we can pull that 2 out. So we're going to say y is equal to 2 times 3 to the second times 3 to the 2/3, because that's what's left over, because 8 minus 6 gives us 2, which is what's left there. We can start cleaning things up. We can say y is equal to 2 times 9 times, and here's where things get funky, 3 stays there, we put a 3 out front, and then it's raised to the second power here. We continue to clean up, and we say y is equal to 18 times, and then this mess, 3, 3, 2. And this is what we end up plugging in. I apologize for how messy this is. Times the cube root of 3 to the second power. And you could continue doing that, either following blue or purple there, just going through and plugging things in. I'm going to put the answers down just so that we can see them, just in case you are somebody working at home and want to get the rest of these. So bear with me one second as I go and do these. 18 times the cube root of 3, 6 times the cube root of 3 to the second, 6 times the cube root of 3, and then here was 2 times our cube root 3 all to the second power. So that's a lot of information in there, so take a second. I'm going to zoom out here so that you can see both problems. It's a lot of repetitive things. Get comfortable with switching square roots or fractions into square roots into fractions, fractions into square roots when they are listed as a power. But we have another short couple problems here, so we're going to go through. We're going to get that all set up right now. All right, our last problem set here is on page 3 of this homework assignment. It is all about simplifying exponents. We're going through, we're rewriting the following expressions using exponent rules and relationships, so that there's only one exponent in the expression. All exponents are positive. Write your answers in exponential form. And then they have an example there. They are not asking us to solve for what 2 to the 7th power ends up being in here. They're saying just write it with a base and a power, as long as that power ends up being a whole number. There's one exception to that in this. But anyway, so we're going to jump right in here, and we're going to start solving these. When we have things that have the same base, we end up, and it's multiplication, we end up adding our power. So we're just looking here, and we're saying that this, oh, that was strange, sorry about that, is 3 to the 7th, and we're done. Both have a base of 3, they're being multiplied, just add your powers. Do not change your base whatsoever in here. Same thing goes for 13. We have a division problem, which means we're just going to do subtraction. Teachers will teach us multiple ways. I like saying always take the larger power and subtract the smallest from it, and then put your base where that is. So in this case, it doesn't really matter because it's our numerator has the largest power. We're going to go through, we're going to write this as 5, and that's 3 minus 2, which is 1. Now we could simplify that to just be 5. That's totally fine if that's what you want to write. You could go through and do that. I don't think that's breaking any rules there. That's an easy thing to simplify. Moving down to here, though, we end up with our first negative power. In order to get rid of that negative power, we're just moving it. We're just saying, all right, if the negative power is in the numerator, we're going to move it to the denominator. We're going to write it as 1 over 2 to the 5th. Reason the 1 goes there is we need to have something that's sitting there. And if we just move 2 to the 5th, there would be nothing, and that's not something that's possible. But we're going to maintain it here. The only weird one in here is that anytime we see something to the 0th power, we automatically change it to be 1, and we call it a day. That kind of breaks the rules for this, but that's where we're going to go. Problem 16. You can do this one of 2 ways. You could multiply across first. You could do the division, whatever it is that you'd like. I'm going to do the multiplying across, and then we'll do the division. You'll get the same answer regardless. So when I go through and I figure out, all right, this is 7 to the 8th power, because just moving right across, because it's 7 to the 5th times 7 to the 3rd. Keep the base of 7, add your powers. Do the same thing in the denominator, 7 to the 6th. Well, this is great, but now we still have two exponents here with the same base. So we're going to now do the subtraction. 7 to the 8th all over 7 to the 6th is just going to be 7 to the 2nd over 1, but we don't need to write that. Same thing that I said in problem 16 at 17. There's multiple ways to go about doing it. I'm going to take care of what's in the numerator first, then I will deal with the denominator. But like I said, multiple ways of going through and getting the correct answer. It's just your choice how you see these problems. So I see 3 to the negative 2nd times 3 to the 5th. Once again, they'll be multiplied, same base, just add the power. So negative 2 plus 5 is going to give us 3 to the 3rd over 3 to the 7th. And now this is where I talked about in a problem, I believe problem 13 or 14. I'm going to always look and take the larger exponent and subtract the smaller. So in this case, I'm saying 3 to the 7th minus 3 to the 3rd. And then I'm going to put it where the larger one was. So 7 is obviously larger than 3. So we're going to go through and we're going to say 7 minus 3 gives us 4. And we're going to leave it in the denominator. That clears out our numerator. So we're going to write in a 1 to get there. So this is everything from our Unit 4 here. If you've got questions, please make sure to see your teachers during office hours. Go ask them questions. But other than that, I hope you all have a fantastic day.